Gallium is a chemical element with symbol Ga and atomic number 31. Elemental gallium does not occur in freeform in nature, but as the gallium, compounds that are in trace amounts in zinc ores and in bauxite. Gallium is a soft silvery metal, and elemental gallium is a brittle solid at low temperatures. If it is held in the human hand long enough, gallium will melt, since it melts at the temperature of about 29.76 A degrees Celsius. The melting point of gallium is used as a temperature reference point. The alloy galinstan has an even lower melting point of 19 A degrees Celsius, well below the freezing point of water. Beginning with its discovery in 1875 through the era of semiconductors, gallium was used primarily as an agent to make alloys that melt at low temperatures. Then, gallium became useful in semiconductors, including as a dopant. Today, nearly all gallium is used in electronics. Gallium arsenide, the primary chemical compound of gallium in electronics, is used in microwave circuits, high-speed switching circuits, and infrared circuits. Gallium nitride and indium gallium nitride, minority semiconductor uses, produce blue and violet light-emitting diodes and diode lasers. Gallium has no known role in biology. Because gallium, and ferric salts behave similarly in biological systems, gallium ions often mimic ions in medical applications. Some pharmaceuticals containing gallium and radiopharmaceuticals have been used rarely. Physical properties. Elemental gallium is not found in nature, but it is easily obtained by smelting. Very pure gallium metal has a brilliant silvery color and its solid metal fractures conchoidally like glass. Gallium metal expands by 3.1% when it solidifies, and therefore storage in either glass or metal containers is avoided, due to the possibility of container rupture with freezing. Gallium shares the higher density liquid state with only a few materials, like water, silicon, germanium, bismuth, and plutonium. Gallium attacks most other metals by diffusing into their metal lattice. Gallium, for example, diffuses into the grain boundaries of aluminium-zinc alloys or steel, making them very brittle. Gallium easily alloys with many metals, and is used in small quantities as a plutonium-gallium alloy in the plutonium cores of nuclear bombs, to help stabilize the plutonium crystal structure. The melting point of gallium, at 302.9146 K, is just above room temperature, and is approximately the same as the average summer daytime temperatures in Earth's mid-latitudes. Gallium's melting point is one of the formal temperature reference points in the International Temperature Scale of 1990 established by the BIPM. The triple point of gallium, at 302.9166 K, is being used by NIST in preference to gallium's melting point. The unique melting point of gallium allows it to melt in one's hand, and then refreeze if removed. This metal has a strong tendency to supercool below its melting point freezing point. Seeding with a crystal helps to initiate freezing. Gallium is one of the metals that are liquid at or near normal room temperature, and can therefore be used in metal in glass high-temperature thermometers. It is also notable for having one of the largest liquid ranges for a metal, and for having a low vapor pressure at high temperatures. Gallium's boiling point, 2673 K, is more than 8 times higher than its melting point on the absolute scale, making it the greatest ratio between melting point and boiling point of any element. Unlike mercury, liquid gallium metal wets glass and skin, making it mechanically more difficult to handle. For this reason, as well as the metal contamination and freezing expansion problems, samples of gallium metal are usually supplied in polyethylene packets within other containers. Gallium does not crystallize in any of the simple crystal structures. The stable phase under normal conditions is orthorhombic with 8 atoms in the conventional unit cell. Within a unit cell, each atom has only one nearest neighbor. The remaining 6 unit cell neighbors are spaced 27, 30 and 39 ppm farther away, and they are grouped in pairs with the same distance. Many stable and metastable phases are found as function of temperature and pressure. The bonding between the 2 nearest neighbors is covalent, hence Ga2 dimers are seen as the fundamental building blocks of the crystal. This explains the drop of the melting point compared to its neighbor elements aluminium and indium. The physical properties of gallium are highly anisotropic, that is, have different values along the three major crystallographical axes A, B and C. For this reason, there is a significant difference between the linear and volume thermal expansion coefficients. The properties of gallium are also strongly temperature dependent, especially near the melting point. For example, the thermal expansion coefficient increases by several 100% upon melting. Chemical properties. Gallium is found primarily in the +3 oxidation state. The +1 oxidation is also attested in some compounds. For example, the very stable GaCl2 contains both gallium I and gallium 3, and can be formulated as GaIGaIICl4. In contrast, the monochloride is unstable above 0 AA degrees Celsius, disproportionating into elemental gallium and gallium 3 chloride. Compounds containing gallium-gallium bonds are true gallium 2 compounds. For example, gas can be formulated Ga24+, S2A2, and the dioxane complex Ga2Cl4, C4H8O2, 2 contains a Ga-Ga bond. Chalcogen compounds. Gallium reacts with chalcogen elements only at relatively high temperatures. At room temperature, gallium metal is unreactive towards air and water due to the formation of a passive, protective oxide layer. At higher temperatures, however, it reacts with oxygen in the air to form gallium 3 oxide, Ga2O3. Reducing Ga2O3 with elemental gallium in vacuum at 500 AA degrees Celsius to 700 AA degrees Celsius yields the dark brown gallium I oxide, Ga2O. Ga2O is a very strong reducing agent, capable of reducing H2SO4 to H2S. It disproportionates at 800 AA degrees Celsius back to gallium and Ga2O3. Gallium 3 sulfide, Ga2S3, has 3 possible crystal modifications. It can be made by the reaction of gallium with hydrogen sulfide, H2S, at 950 AA degrees Celsius. Alternatively, Ga-OH3 can also be used at 747 AA degrees Celsius, 2 Ga-OH3 plus 3 hours, 2S a Ga-2S, 3 plus 6 hours, 2O, reacting a mixture of alkali metal carbonates and Ga-2O3 with H2S leads to the formation of thioglylates containing the Ga-2S4, 2-anion. Strong acids decompose these salts, releasing H2S in the process. The mercury salt, HgGa2S4, can be used as a phosphor. Gallium also forms sulfides in lower oxidation states, such as gallium 2 sulfide and the green gallium I sulfide, the latter of which is produced from the former by heating to 1000 AA degrees Celsius under a stream of nitrogen. The other binary chalcogenides, Ga2Se3 and Ga2Te3, have zinc blende structure. They are all semiconductors, but are easily hydrolyzed, limiting their usefulness. Aqueous chemistry. Strong acids dissolve gallium, forming gallium 3 salts such as Ga2SO4 3 and Ga-NO3 3. Aqueous solutions of gallium 3 salts contain the hydrated gallium ion, Ga-H2O6 3+. Gallium 3 hydroxide, Ga-OH3, may be precipitated from gallium 3 solutions by adding ammonia. Dehydrating Ga-OH3 at 100 AA degrees Celsius produces gallium oxide hydroxide, GaO-OH. Alkaline hydroxide solutions dissolve gallium, forming gallate salts containing the Ga-OH, a 4-anion. Gallium hydroxide, which is amphoteric, also dissolves in alkali to form gallate salts. Although earlier work suggested Ga-OH3-6 as another possible gallate anion, this species was not found in later work. Pnictogen compounds. Gallium reacts with ammonia at 1050 AA degrees Celsius to form gallium nitride, GaN. Gallium also forms binary compounds with phosphorus, arsenic, and antimony, gallium phosphide, gallium arsenide, and gallium antimonide. These compounds have the same structure as ZnS, and have important semiconducting properties. GAP, GaAs, and GaSb can be synthesized by the direct reaction of gallium with elemental phosphorus, arsenic, or antimony. They exhibit higher electrical conductivity than GaN. GAP can also be synthesized by the reaction of Ga2O with phosphorus at low temperatures. Gallium also forms ternary nitrides. For example, Li, 3Ga plus N, 2 Li, 3Ga N, 2. Similar compounds with phosphorus and arsenic also exist, Li, 3Gap, 2 and Li, 3Ga-As, 2. These compounds are easily hydrolyzed by dilute acids and water. Halides. Gallium, 3, oxide reacts with fluorinating agents such as HF4F, 2 to form gallium, 3, fluoride, GaF, 3. It is an ionic compound strongly insoluble in water. However, it does dissolve in hydrofluoric acid, in which it forms in a duct with water, GaF, 3 at 3 hours, 2O. Attempting to dehydrate this adduct instead forms GaF, 2ONH, 2O. The adduct reacts with ammonia to form GaF, 3 at 3NH, 3, which can then be heated to form anhydrous GaF, 3. Gallium trichloride is formed by the reaction of gallium metal with chlorine gas. Unlike the trifluoride, gallium, 3, chloride exists as dimeric molecules, Ga, 2 centiliters, 6, with a melting point of 78 AA degrees Celsius. This is also the case for the bromide and iodide, Ga, 2Br, 6 and Ga, 2I, 6. Like the other group 13 triolides, gallium, 3, halides are Lewis acids, reacting as halide acceptors with alkali metal halides to form salts containing Ga-XA, 4 anions, where X is a halogen. They also react with alkyl halides to form carbocations and Ga-XA, 4. When heated to a high temperature, gallium, 3, halides react with elemental gallium to form the respective gallium, I, halides. For example, GaCl, 3 reacts with Ga to form GaCl, 2 Ga plus GaCl, 3 GaCl. At lower temperatures, the equilibrium shifts toward the left and GaCl disproportionates back to elemental gallium and GaCl, 3. GaCl can also be made by the reaction of Ga with HCl at 950 AA degrees Celsius. It can then be condensed as red solid. Gallium, I, compounds can be stabilized by forming adducts with Lewis acids. For example, GaCl plus AlCl, 3 a Ga plus, AlCl, 4, a, the so-called gallium, 2, halides, Ga-X, 2, are actually adducts of gallium, I, halides with the respective gallium, 3, halides, having the structure Ga plus, Ga-X, 4, a. For example, GaCl plus GaCl, 3 a Ga plus, GaCl, 4, a, hydrogen compounds, like aluminium. Gallium also forms a hydride, Ga-H, 3, known as gallin, which may be obtained by the reaction of lithium galanate, Li-Ga-H, 4, with gallium, 3, chloride at a 30 AA degrees Celsius, 3 Li-Ga-H, 4 plus GaCl, 3 of 3 Li-Cl plus 4 Ga-H, 3, in the presence of dimethyl ether as solvent, Ga-H, 3 polymerizes to Ga-H, 3, N. If no solvent is used, the dimer Ga, 2 hours, 6 is formed as a gas. Its structure is similar to diboron, having 2 hydrogen atoms bridging the 2 gallium centers, unlike I plus or minus Al-H, 3 in which aluminium has a coordination number of 6. Gallin is unstable above a 10 AA degrees Celsius, decomposing to elemental gallium and hydrogen. History: in 1871, existence of gallium was first predicted by Russian chemist Dmitry Mendeleev, who named it aluminium on the basis of its position in his periodic table. He also predicted several properties of the element, which correspond closely to real gallium properties, such as density, melting point, oxide character and bonding in chloride. Gallium was discovered spectroscopically by French chemist Paul-Émile Lecoq de Bois-Baudran in 1875 by its characteristic spectrum in an examination of a sphelerite sample. Later that year, Lecoq obtained the free metal by electrolysis of its hydroxide in potassium hydroxide solution. He named the element Gallia, from Latin Gallia meaning Gaul, after his native land of France. It was later claimed that, in one of those multilingual puns so beloved of men of science in the 19th century, he had also named gallium after himself, as his name, Lecoq, is the French for the rooster, and the Latin for rooster is gallus. However, in an 1877 article Lecoq denied this supposition. From its discovery in 1875 up to the era of semiconductors, its primary uses were in high-temperature thermometric applications and in preparation of metal alloys with unusual properties of stability, or ease of melting. Some being liquid at room temperature or below. The development of gallium arsenide as a direct band-gap semiconductor in the 1960s ushered in the most important stage in the applications of gallium. Occurrence: gallium does not exist in free form in nature, and the few high gallium minerals such as gallite are too rare to serve as a primary source of the element or its compounds. Its abundance in the Earth's crust is approximately 16.9 ppm. Gallium is found and extracted as a trace component in bauxite and to a small extent from sphelerite. The amount extracted from coal, dispore and germanate in which gallium is also present is negligible. The United States Geological Survey estimates gallium reserves to exceed 1 million tons, based on 50 ppm by weight concentration in known reserves of bauxite and zinc ores. Some flue dusts from burning coal have been shown to contain small quantities of gallium, typically less than 1% by weight. Production: gallium is a byproduct of the production of aluminium and zinc, whereas the sphelerite for zinc production is the minor source. Most gallium is extracted from the crude aluminium hydroxide solution of the Bayer process for producing alumina and aluminium. A mercury cell electrolysis and hydrolysis of the amalgam with sodium hydroxide leads to sodium gallate. Electrolysis then gives gallium metal. For semiconductor use, further purification is carried out using zone melting, or else single crystal extraction from a melt. Purities of 99.9999% are routinely achieved and commercially widely available. In 1986, the production was estimated at 40 tons. In 2007 the production of gallium was 184 tons with less than 100 tons for mining and the rest from scrap recycling. By 2012 world production of gallium was an estimated 273 metric tons. In January 2013, the market price of gallium lay at $580 USD per kg, while by autumn that year, it had dropped to around $280 USD per kg, or just under $9 USD per ounce. Applications: the semiconductor applications dominate the commercial use of gallium, accounting for 98% of applications. Your next major application is for gadolinium gallium garnets. Semiconductors. Because of this application, extremely high purity gallium is commercially available. Gallium arsenide and gallium nitride used in electronic components represented about 98% of the gallium consumption in the United States in 2007. About 66% of semiconductor gallium is used in the U.S. in integrated circuits, such as the manufacture of ultra-high-speed logic chips and MESFETs for low-noise microwave preamplifiers in cell phones. About 20% is used in optoelectronics. Worldwide, gallium arsenide makes up 95% of the annual global gallium consumption. Gallium arsenide is used in optoelectronics in a variety of infrared applications. Aluminium gallium arsenide is used in high-powered infrared laser diodes. As a component of the semiconductors indium gallium nitride and gallium nitride, gallium is used to produce blue and violet optoelectronic devices, mostly laser diodes and light-emitting diodes. For example, gallium nitride 405 nm diode lasers are used as a violet light source for higher density compact disc data storage, in the Blu-ray disc standard. Multi-junction photovoltaic cells, developed for satellite power applications, are made by molecular beam epitaxy or metal-organic vapor phase epitaxy of thin films of gallium arsenide, indium gallium phosphide or indium gallium arsenide. The Mars exploration rovers and several satellites use triple-junction gallium arsenide on germanium cells. Gallium is also a component in photovoltaic compounds, say, S2, for use in solar panels as a cost-efficient alternative to crystalline silicon. Galinstan and other alloys, gallium readily alloys with most metals, and has been used as a component in low-melting alloys. A nearly eutectic alloy of gallium, indium, and tin is a room-temperature liquid that is available in medical thermometers. This alloy, with the trade name Galinstan, has a low freezing point of 19 degrees Celsius. It has been suggested that this family of alloys could also be used to cool computer chips in place of water. Gallium alloys have been evaluated as substitutes for mercury dental amalgams, but these materials have yet to see wide acceptance. Because gallium wets glass or porcelain, gallium can be used to create brilliant mirrors. When the wetting action of gallium alloys is not desired, the glass must be protected with a transparent layer of gallium oxide. The plutonium used in nuclear weapon pits is machined by alloying with gallium to stabilize its I phase. Gallium added in quantities up to 2% in common solders can aid wetting and flow characteristics. Alloys of Al and Ga have been evaluated for hydrogen production. It is used as the alloying element in the magnetic shape memory alloy NiM-Ga. Biomedical applications. Although gallium has no known role in biology, it mimics iron. The gallium ion localizes to and interacts with many processes in the body in which iron is manipulated. As these processes include inflammation, which is a marker for many disease states, several gallium salts are used, or are in development, as both pharmaceuticals and radiopharmaceuticals in medicine. When gallium ions are mistakenly taken up by bacteria such as Pseudomonas, the bacteria's ability to respire is interfered with and the bacteria die. The mechanism behind this is that iron is redox active, which allows for the transfer of electrons during respiration, but gallium is redox inactive. Gallium maltolate has high bioavailability and the gallium is antiproliferative to pathologically proliferating cells, particularly cancer cells and some bacteria, due primarily to its ability to mimic ferric iron. Gallium nitrate has been used as an intravenous pharmaceutical to treat hypocalcemia associated with tumor metastasis to bones. Gallium is thought to interfere with osteoclast function. It may be effective when other treatments for malignancy-associated hypocalcemia are not. Gallium maltolate, an orally absorbable form of gallium ion, is in clinical and preclinical trials as a potential treatment for a number of types of cancer, infectious disease, and inflammatory disease. A complex phenol Ga compound MRO45 was found to be selectively toxic to parasites that have developed resistance to chloroquine, a common drug against malaria. Both the Ga complex and chloroquine act by inhibiting crystallization of hemazoan, a disposal product formed from the digestion of blood by the parasites. Radiogallium salts, gallium-67 salts such as gallium citrate and gallium nitrate are used as radiopharmaceutical agents in a nuclear medicine imaging procedure commonly referred to as a gallium scan. The form or salt of gallium is unimportant. For these applications, the radioactive isotope 67 Ga is used. The body handles Ga3+ in many ways as though it were iron, and thus it is bound in areas of inflammation, such as infection, and also areas of rapid cell division. This allows such sites to be imaged by nuclear scan techniques. This use has largely been replaced by fluorodeoxyglucose for positron emission tomography, PET scan and indium-111 labeled leukocyte scans. However, the localization of gallium in the body has some properties which make it unique in some circumstances from competing modalities using other radioisotopes. Gallium-68, a positron emitter with a half-life of 68 minutes, is now used as a diagnostic radionuclide in PET-CT when linked to pharmaceutical preparations such as dotatate, a somatostatin analog used for neuroendocrine tumors investigation, and dotatate, a newer one, used for neuroendocrine metastasis and lung neuroendocrine cancer, such as certain types of microcytoma. Gallium-68's preparation as a pharmaceutical is chemical, and the radionuclide is extracted by elution from germanium-68, a synthetic radioisotope of germanium, in gallium-68 generators. Other uses: magnesium gallate containing impurities, is beginning to be used in ultraviolet activated phosphor powder. Neutrino detection. Possibly the largest amount of pure gallium ever collected in a single spot is the gallium-germanium neutrino telescope used by the SAGE experiment at the Baksan Neutrino Observatory in Russia. This detector contains 57 tons of liquid gallium. Another experiment was the Galex neutrino detector, operated in the early 1990s in an Italian mountain tunnel. The detector contained 12.2 tons of watered gallium-71. Solar neutrinos caused a few atoms of 71 Ga to become radioactive 71 Ge, which were detected. The solar neutrino flux deduced was found to have a deficit of 40% from theory. This was not explained until better solar neutrino detectors and theories were constructed. As a liquid metal ion source for a focused ion beam. For example, a focused gallium ion beam was used to create the world's smallest book, Teeny Ted from Turnip Town. In a classic prank, scientists would fashion gallium spoons and serve tea to unsuspecting guests. The spoons melt in the hot tea. As an additive in glide wax for ski and other low-friction surface materials. US 5,069,803, Sugimura, Kentaro. Shoji Hasemoto and Takayuki Ono, use of a synthetic resin composition containing gallium particles in the glide surfacing material of skis and other applications, issued 1995. Precautions: the Ga3 ion of soluble gallium salts tends to form the insoluble hydroxide when injected in large amounts, and in animals precipitation of this has resulted in renal toxicity. In lower doses, soluble gallium is tolerated well, and does not accumulate as a poison. While metallic gallium is not considered toxic, the data are inconclusive. Some sources suggest that it may cause dermatitis from prolonged exposure. Other tests have not caused a positive reaction. Like most metals, finely divided gallium loses its luster and powdered gallium appears gray. Thus, when gallium is handled with bare hands, the extremely fine dispersion of liquid gallium droplets, which results from wetting skin with the metal, may appear as a gray skin stain. See also, references. External links: Gallium at the periodic table of videos, material safety data sheet at ashialloys.com, high-resolution photographs of molten gallium, gallium crystals and gallium ingots under Creative Commons license, www.lentech.com. A Euro textbook information regarding gallium, environmental effects of gallium, price development of gallium 1959. A Euro 1998, Gallium a smart metal. United States Geological Survey, technology produces hydrogen by adding water to an alloy of aluminum and gallium, thermal conductivity.